Okay, so we've seen how to compute the first principal component, and the description was that it provides a summary of the data. It's got the most variance. Well, you can go further. If you've got p variables, you can now ask for a second principal component, which also has large variance, but unless you want to get the same one as the first, you have to put some constraint. So the constraint, the natural constraint, is that this second variable be uncorrelated with the first. So it's going to tell you different information about the data, and subject to being uncorrelated, it's going to have largest variance. Okay, so that's a problem which we can phrase in pretty much the same way. It's going to be a linear combination. We've got it now indexed by 2 instead of 1. There's a sub 2 there, and subject to that constraint of being uncorrelated, we wanted to maximize the variance. Now, there's some interesting math that comes with this. It turns out that being uncorrelated also means that the alphas, the phis, I beg your pardon, that define the principal component as vectors, right? Those are the loading vectors. So the phis for the second component defines a vector that's orthogonal to the phis for the first component. So it's just a property of the solution. And so we can characterize that lack of correlation as orthogonality of the phis. And the solution, turns out, also comes from the singular value decomposition of x. So the second principal component's defined by the second right singular vectors. And there's going to be a third component, a fourth component, and so on. That sequentially maximize variance subject to being uncorrelated with all the previous ones. And it turns out that you can have at most min n minus 1 or p principal components. So n is the number of data points. Sometimes p is bigger than n, and if that's the case, then we're restricted by n, but otherwise we're just restricted by p, the number of variables. So we get a complete decomposition of the data matrix in terms of its principal components. So as an illustration, we're going to show you an example using some data on USA arrests. So for each of the 50 states in the United States, we've got their number of arrests per 100,000 residents for each of 3 crimes: assault, murder, and rape. And we also have measured the urban population, the percentage of the population in each state living in urban areas. So there's 50 observations. So each of the principal components are going to be n vectors with length 50, because they're new variables. And we'll get at most 4 principal components, and each of them will be described in terms of loading vectors of length p equals 4. In this case, we actually standardized the variables before we did the principal components to have mean 0 and standard deviation 1. That's a fairly standard practice, and we'll get back to that in a moment, but let's first look at the results. So here's the results. This picture is called a biplot. And it's a way of displaying the principal components and the loadings in a single plot. So each of the blue, well, they're not points, but marks on the picture is a state, and so their names are there. The origin is at the center over here, so everything's been centered with respect to the origin. And on the plot as well, what we see are the loading vectors. So this plot is the plot of the first principal component along the horizontal axis here, and the second principal component on the vertical axis. So we plot the first 2 principal components, which is fairly standard because, those are the most 2 important ones. And so in order to understand the principal component, so each observation, which is a state, has a score on the principal component. And so some are large and positive and some are negative. And then to understand these scores, we look at the loadings. And so the loadings are plotted as vectors here because we've got, for each variable, we've got its loading on the first principal component and the second principal component, so that allows us to plot it as a vector in this space. And what we read from this is that the first principal component has got positive loadings, large positive loadings on rape, assault, and murder. So all of the crimes are positive loadings on the first principal component. So that tells us that this direction on the positive side is loaded up on all 3 crimes, sort of roughly about the same amount. Okay, and so these are going to be high crime regions, these are going to be low crime regions. And so now you can look at where the states lie. For example, Florida is sitting right out on the first principal component, so that's a high crime area, and so on. So you look at the positions where states project to see how they relate to the principal component. Now the second principal component seems to get largely loaded on urban population. So this is a high urban population, this is low urban population. And you can even interpret things like rape seems to be on the positive side in high urban populations than in low urban populations. So again, this biplot is a picture that lets you both display the first two principal components and also display the loadings and give you a way of interpreting the picture.
So, Trevor, what does it mean for like a component being -3? What is that?
Well, -3 means that you low down. The actual units are somewhat standardized units, but it means you on the negative scale in the crime rate. So these are low crime areas. And so some of the extreme low crime areas are, if I can read the text, there's Maine is a low crime area.
New Hampshire, Iowa,
Yeah.
Okay.
Okay, so here's some details that explain the figure, which we've just gone through. You can read it in your own time. It's customary also to produce a table of the loadings, and so this just summarizes what we saw in the picture. So we see that in the first principal component, pretty much equal loadings on murder, assault, and rape, whereas urban population has somewhat of a lower loading. Is the second principal component. Urban population's got a high loading, and murder's got quite a high loading as well. So, that's a negative loading, but rape was a slightly positive loading. So you can actually look at the numbers, but it's often better and more useful to look at them graphically. Okay, so that's the primary use of principal components to come up with summaries of the data that explain mostly what's going on. But there's another view of principal components, and that's in terms of approximating a cloud of data by a low-dimensional hyperplane. And it turns out these two views are equivalent to each other. So here's a data set. It's an artificial data set. In the left-hand plot, we see some points. They're meant to be, we're visualizing them in three-dimensional space. And what we've shown here is a two-dimensional hyperplane that's meant to approximate those points. Now the points are colored, but that's just to help us explain what's going on. This seems to be like a clustering. But what we see is that this hyperplane sort of passes through the middle of these points, and we're asking for a hyperplane that gets as close as possible to the points. And what we mean by that is that if we take each point and compute the shortest distance to the hyperplane and sum the squares of those distances, we want the hyperplane that gets closest to the data in that sense. And it turns out that the hyperplane's defined in terms of the two largest principal components. In other words, the direction vectors that define the hyperplane, if you think of having two direction vectors in the hyperplane, it'll be orthogonal to each other, those are also the two direction vectors of the largest two principal components. And it sort of makes sense. Getting closer, we've got we're in 3 dimensions here, so we've got 3 variables. To get closest to the data, to find the plane closest to the points, we're asking actually that the projection of the points in the plane are spread out as much as possible. That'll be a characteristic of the solution. In other words, spread out means as much variance as possible. So that gives you an intuition of why the two principal components also characterize this solution.
Now, I'm confused here. What you described about being close to points sounds to me like least squares regression, which we covered earlier. So it's a difference somehow?
Yeah, that's a good question, Rob. Least squares regression is also found in a hyperplane that gets close to the data in some sense. But there close is defined just in terms of distance from the hyperplane to y, the response, which was the supervising variable. But here we don't have any y. So here it's shortest distance of the hyperplane to the x's themselves.
Could you draw a picture into a scatter plot to show this?
Could I draw a scatter plot to show this?
The distinction between those two.
Okay, so for linear regression, we have y, and, well, I can only draw one x. Maybe I can draw a second x in the picture. So that's x2, x1. This is x1. and we got a whole lot of points. And now we find a hyperplane, okay? But in linear regression, we focus in just on this distance over here, which is not perpendicular to the hyperplane. It's just distance in the y direction, right? Whereas in principal components here, there's no special variable that's a y, and so we define distance in terms of the perpendicular distance to the hyperplane.
Right.
How's that picture, huh?
A lot better than I could have done, but okay.
All right. So this slide here just describes what we've just gone through in detail. Now, I deferred this point. Scaling of the variable matters. So here's our first two principal components in our biplot again. But this was computed when we standardized each of the variables to have unit variance. What if we didn't do that? Well, you get a very different picture then. Here, the picture, the first principal component seems to be mostly a salt. Well, it turns out that the variable a salt had by far a much bigger variance in the original data set than any of the other variables. It's just the units in which it was measured, and so it just dominates the first principal component. And if you have variables that are actually measured in different units, it's quite easy to have one variable that just on its own has a way bigger variance than the rest, and it will dominate the principal components. So if you want to avoid the effect of units or just individual variables having a big variance, then you standardize the variables. And in that case, what you're dealing with is variables all measured on an equal scale, and now you can really see which components add together to give you large variance. So there's also associated with principal components a decomposition of variance. So we start off, we got our variables, and we can talk about the total variance that's about to be explained, which is the sum of the variance of all the variables. Okay? And if the variables have been centered to have mean 0, that's given by this expression over here. 1 over n summation xij squared is just going to be, this is going to be the variance of the jth variable, and we sum that over the p variables. And the variance of the mth principal component is going to be the sum of the zim squared. Again, the zi's are going to have mean 0 because the original x's had mean 0. They'll inherit that property as well. So this is an expression for the variance of the mth principal component. Okay. Now, you can show that the sum of the variances of all the x's is the same as the sum of the variances of all the z's. That's just a mathematical property. And so we can talk about the proportion of variance explained by looking at the variance of an individual z relative to the sum of the variances. And that gives you an idea of the importance of each of the components. Okay? So, and that'll be a quantity that's between 0 and 1, right? Because the sum of the variance of the z's is in the denominator. Okay. So this left plot on the crime data shows the proportion of variance explained by each of the principal components. So the first one explains about 0.6 of the variance, or 60% of the variance. The second component explains just over 20% of the variance, and so on. So these necessarily decrease because, after all, we've been asking for the first principal component to explain the most of the variance. The second one has to be uncorrelated with the first, and so these necessarily have to go down. And sometimes we plot the cumulative percentage of variance explained, which is, in this case, this is the percentage of the first principal component of the total variance. This is the percentage of the first two, and so on. And the idea is that we want to know basically when to stop, how many components we need. And so we're going to be happy to stop if we've explained most of the variance. So if let's say the first two principal components explain 95% of the variance, we'd be happy to stop there. Here it looks like we need the first three principal components. Because there's no real hard and fast rules on how many components you need. So this percentage variance explained is a one way of sort of getting a feeling of when you've got most of the variance explained. So the question that's just come up is how many components should we use? And so there's no real simple answer. One thing you might think is, why not use cross-validation? Is that available for this purpose? Well, it's not really. And you might think, why not? We use cross-validation in regression. It was very useful there. Well, we don't have a response here. Cross-validation was used when we had a response and we could see how well we were predicting the response when we left some data out. But we don't have a response here. So there's no supervising variable to help us. So does that mean cross-validation is completely ruled out? Well, not really. One of the uses of principal components, which we touched on earlier in this course, was in regression. When you had a lot of variables, you could use principal components to reduce the data to a few important variables, i.e. the first few principal components, and use them in the regression instead. Well, now you can use cross-validation because we do have a response in that case. And so you might decide how many principal components you need to use in the regression, and you could use cross-validation to help you decide that. But there you have a supervising response. And as I mentioned in the previous slide, that's sometimes called a scree plot, and you can look for an elbow in the scree plot. So which is the percent variance explained plot, right? So if your percent variance explained looked like this, if this was 1 and this was 0, and if the first one was up there, the second one was over there, and then the rest were all down here, you'd say, well, 2 principal components seems to be explaining a lot. Because there's a big elbow here. So if you look for elbows in the scree plot, that's often helpful. So that's the end of principal components. Again, principal components, one of the most useful tools we have in applied statistics. It's used all over the place, and it's got many other applications as well, which we won't touch on here. So it's a very useful tool. In the next session, we're going to talk about the second most useful tool, or another very important tool, which is clustering, and we'll tell you about 2 different methods for clustering.